Hello everyone, and welcome to the NEATEC Electronics Series. This video is about the product of sums, so let's get started. So now, as you can see, I've changed the title. And the title is different, isn't it? It's no longer SOP, it's now POS, right? So it's the product of the sums, all right? Now this is different, all right? So we have to go through a little bit of a proof. So I want to show you how it works, okay? So for the product of the sums, we're going to use the values when y equals 0. So we'll use this one, we use this one, this one, this one, and this one, okay? So if we're going to write this correctly, right? Let's just write it right. So we're going to say when y is 0, which is y bar, it's going to be 0 when we're going to do the same way we did it with the SOP method, right? It's going to be when a is 0, we're doing this one right here, okay? A is 0, and B is 0, and C is 1, right? Or, let's do this one now, right? We'll do this one right here, right? That one's going to be when A is 0, okay, A bar, right? B, C bar, right? There we go, we just took care of that one. Or A, when A is 1, and B is 0, and C is 1, that's A, B bar, C, right? Or, let's come over here, it's this one next, right, you guys? So it's going to be when A is 1, and B is 1, and C is 0, right? Or, finally we're down here, aren't we? When A and B and C are 1. There we go, right? So we have 1, 2, 3, 4, 5 terms, right? A bar, B bar, C, or A bar, B, C bar, or A, B bar, C, or A, B, C bar, or A, B, C. Right, and obviously you can see that each one of these groups of 3 like this, these are product terms, okay? So now I want to bring something to you and to remind you of something, okay? Let's remember De Morgan's theorem, right? So if we're looking at De Morgan's, okay, if I say we have a 3-input OR gate with an inverted output, we would have X plus Y plus Z, right? That's pronounced actually X or Y or Z. There's your OR gate. And suppose it has an inverted output, so I put a line over it. So that's a NOR, isn't it? That's a NOR gate. Well, what's that going to equal? Well, that's going to equal an AND gate. That's an AND gate, isn't it? A 3-input AND gate with each of the inputs inverted and the output not inverted because it's inverted in the beginning, right? So we know that one. What about if you have a NAND gate? In other words, an AND gate with an inverted output. Let's just write that down. X, Y, Z. We have a bar over both of them, right? And this, good. Now what's that going to equal? Well, we know it's going to equal an OR gate, right? So it's going to be X plus Y or Z. I apologize, when I write the plus sign, sometimes I say plus, sometimes I say or. I'm trying to standardize, but you understand when I write a plus sign, it means or. That means an OR gate, right? So we don't have an inverted output, but obviously each of the inputs are going to be inverted, right? So let's just remember that. So what we did is we have an expression here for y bar, right? Now, we don't want to have this expression to be in terms of y bar. We want it to be in terms of y. So I can say y is going to equal y bar, right? That right there is y bar. I'm just bringing it down, right? And guess what? I'm going to invert it. I'm going to put another bar on top of it. So it's y bar bar. Get it? Now that's going to equal what you have here, this whole thing. All right? It's going to equal that. I'll show you this in a minute. It's going to equal that whole thing. So if I take this, I'm going to bring that down. All right? I just copied it. That's all I did. And what do you think I'm going to do to it? Put a bar all over it, right? Remember, what you do on the left side of the equal sign, you have to do on the right side of the equal sign, okay? You got that now? Now, what we have here, if you look at your first theorem right here, if you look at this, you can think of this part right here as the first part, right? It's an OR gate that has a bar over it. So all we're going to do is rewrite that in this form right here, okay? So this one will equal A bar, B bar, C, with a bar over all of it. Got it? Now, if you notice, we went from an OR gate up here. You're an OR gate over here in this part, right? This is an OR gate. This is an AND gate. Get it? All right. Now let me just remove those things because I don't want to confuse anyone. So then we're going to write the next one. What's this next one going to be? It's going to be A bar, B, C bar, the bar over it. Got it? Let's continue. Let's just continue. We have A, B bar, C, bar over everything, right? And now we've got to continue with the next one. It's going to be A, B, C bar, the bar over it. And then finally we'll have A, B, C, with a bar over it. Get it? All right. Now, we're going to use the second equation of De Morgan's theorem, okay? So now we can say that this term right here this is going to equal A or B or C bar. Get it? If you look what's happening here, we have X, Y, and Z, right? Let me do this for you. Got it? That with a bar over it, right? It's a NAND gate. That's what we have here. It's just a NAND gate, right? Actually, we have a NAND gate with two inverted inputs, but it's fine. So for De Morgan's theorem, you just turn it into an OR gate. That's what we did. And we invert the outputs. Well, if you invert the B, it's like a B bar bar, and the bars cancel, just like we did up here with the Y, right? And the same thing with A, but C, you invert that input, right? So let's continue. What's the next one, right? We're gonna have to invert each one of these, right? So now this next one's going to be A or B bar, right? Or C, right? Or A bar plus B C bar, right? We're going to have A bar. I'm sorry, that should be a B, right? B bar plus C. And then the last one is going to be plus B bar plus C bar. All right? Let me check. I hope I didn't make any mistakes. A, B, C bar. That's right. A, B bar plus C. That's right. A bar, B, C bar. That's right. A bar, B bar, C. That's right. And A bar, B. There you go. There you go. That's what it's equal to, right? Now, there's your equation for Y. Get it? Y equals this value here. Now, let's draw the circuit, shall we? And I'm going to have to get some space here. So I'm going to have to remove De Morgan's theorem and things. So sorry, De Morgan. We needed the real estate. Now let's take the final expression we have here and move it up here for you. Okay? So we have A, B, and C, right? Well, let's do the same thing we did before. We're going to have A, B, and C. A is going to look like this. And we'll have B. And then we'll have C. And then we'll have C bar. remember, I'm drawing inverters, and the inverters are pointing down, right? This is simply to conserve real estate when you're drawing your circuits, right? Now remember, each one of these gates here, right? This is an OR gate, isn't it? So let's start to draw it, right? This will be an OR gate. Draw one right here. I'm going to have to draw 5 of them, right? Eventually. So that's going to come, one's going to go to A. This one here, we'll go from here. One's going to go to B. One's going to go to C bar. So we got that one, right? Let's do the next one. That's a bad gate, isn't it? So this one's going to go to A. This one's going to go to B bar. And this one's going to go to C, right? Got that one. Right? Let's draw another one. Now this is going to go to A bar, B, and C bar, right? We'll go A bar, B, C bar, all right? Let's draw another one. Now this is going to be A bar, B bar, C, right? A bar, B bar, C, right? And finally, we're now at this one right here. This is your last one, right? So draw it right here. What's that one? A bar, B bar, C bar, right? There they are. Now notice that they're all ANDed together, right? By the way, let's show you. This is a sum, isn't it? Is it this one right here? That's a sum. This right here. That's a sum. That's a sum. And this is a sum, isn't it? But between them, we don't have a dot. I didn't put a dot there, but this is a product, isn't it? Same with here, right? Same here. Do you see where this comes from? It's a product of the sums. Get it? Each sum is multiplied. Well, it's not actually multiplied, it's ANDed, but you understand it. It's a product, right? So really, what happens next is all of these outputs into one big ol' AND gate. They're all ANDed together. And here you have y, okay? And y equals the expression above, okay? Now this is termed product of sums, okay? Let me just show you something here because I don't want you to miss the pattern here. You can see, obviously, that each one of these terms over here, right? For example, this term, let's just look at this term right here. It's the lowest term. So this right here, this term is actually A bar or B bar or C bar. Get it? This term right here, and it comes from right here, this is going to be what? A bar or B bar or C, right? Now this one is going to come from this one, right? So we write this one. It's going to be A bar or B or C bar. Get it? Let me make that C bar look just a little bit more presentable, okay? Here's your C bar. Now, if we're looking at this one, that's going to be up top here. This is going to be, if we're looking at this one, this is going to be A or B bar or C. And finally, this one right here, that's going to be, let me get a little bit of space over here, all right? A little bit of space. That's going to be A or B or C bar. Do you see the pattern? If you're looking for the zeros, right, the POS, you have to invert each one of the inputs. So if you look at the input on your truth table, this right here is A bar, B bar, C. And here we have A, B, C bar. So we just took the complement of each of the inputs and you OR them together. There's your gate. Okay, and we did that with each one of these inputs. You can see that for yourself. And they're combined, they're ANDed together. That's why you called it the product of the sums. The sums of the product was different, all right? But those are the two methods that we're studying right now, product of the sums and sums of the products, for generating a circuit from a truth table, all right? All right, everyone. See you soon.